and we'll enjoy some more of our second part of the calculus class, right? So we already tried to do various types of rotations. We rotated in order to produce three-dimensional figures so we could find its volume. That was the plan. Find volume of three-dimensional figure produced by rotation. And we rotated about y-axis last time. I traced this particular example with a beautiful picture. And we also rotated about x-axis. And not just about x-axis, we also rotated about any horizontal line. And that's something that we did. So horizontal lines. So today we'll trace rotations about vertical lines. I say, well, when we're gonna trace rotations about slant lines? Well, we're never gonna do that. We used to do it. It was class calculus 4 a while ago. That's where we utilized methods of so-called linear algebra to produce those rotations. Very tedious, so they decided to cancel this portion of math for the colleges. But if you be curious, I'm sure you will be able to find it if you go to the 4-year school, and that's what they're doing there. So the point of story, the calculus starts and it develops, and there are various things that being added, but it's all been developed 100+ years ago. So it's already quite old theory. So but we just take it and enjoy it. And that's why actually I say that it doesn't really matter what textbook we are using because it's all the same stuff. All problems are very similar. But of course, you can create more challenging exercise if you produce nasty arithmetic. That's the only thing. But nice arithmetic that has 0, 1 for the limits of integration, and if we rotate about x-axis or y-axis is the best. So I'd like to rotate about some other vertical line. So looks like vertical rotations appear in the exercise group here, 19 through 22. Looks like there is nothing in tricks, so I'll just take one of those and try to rotate. So how about 21, for example? So they're all, I think, the same. So I just select a problem and try to enjoy it. So exercise number 21, I think, would be good to do. And we're still in section 7.2. And for this particular textbook, it's a page, whatever we have here for the page. Where are the pages? Here it is, 489 page. But I know there are various editions of the same textbook, so you might not have a page 489 for this particular exercise. That's why I don't try. So section 7.2 is that we have. So anyways, 21 says, use the parabola x is equal to y squared. It is a parabola because looks like we switch x and y when you graph y is equal to x squared. It's a parabola along y-axis, and x is equal to y squared will be the parabola that opens along x-axis. So it is quite straightforward, right? And then we also have x is equal to 4, and that's the line which is vertical line with equation x is equal to 4. So of course, it's always a good idea to know the y coordinates of those points of intersection of those figures, and looks like 4 when you use for x, right? Then y could be either +2 or -2. When you square root, you always have two answers with a plus or with a minus sign. And that's why it's not a function, the parabola, because it has failed vertical line test. But that's fine, because what we care about is not if it's a function or not, but taking this piece, and now we need to rotate. And now here comes a different part, because we're rotating it not about the axis. We're rotating it about the vertical line, because it has equation x is equal to 5. So it is very important to make a picture correctly, because otherwise it'd be pointless to do the whole thing if you don't see what is that you need to find. Moreover, my goal here is to convince you that it is very doable, nothing is tricky, and for the little midterm that I plan to give you, I will give you something very, very standard. I'm not going to give you trig exercises. I know sometimes it's challenging to graph these things, but I'm not planning to give you a hard time on the exam. I will give you some with parabolas. I'm sure you know how to graph. Right? So what do I do now? Well, I rotate. I rotate this chunk produced by highlighted in blue, and I rotated about line is equal to x is equal to 5. So I produce like what, waves or some kind of thing that is probably like a ball, but not a ball because it's produced by parabola. And also I drill through the like cylinder. Actually, it is a cylinder. So that's the way we get. Now, we're using our disk, or since it's not just a disk, but if you decide to see the slice when you drill through, it's going to be a disk with a hole, or they say it's a washer. When you gonna slice it. So what you're gonna slice is along y-axis from -2 to +2. -2 to positive, and since it's along y-axis, our variable of integration will be y. Because we're slicing along the y-axis, right? Along the vertical axis. So it is always going to be y. And then we need to take these washers and imagine their volumes. So to get the volume of it, I'm going to make a better picture just of that thing that we see. It resembles to disk, right? And the thickness is delta y. That's why we have dy, because we again slicing along y-axis. So we just took one of those. And then, of course, we also drill the hole through. And the hole is not going to change. For the hole, we're going to have the same exact radius. I'll call it as a little r, radius of the hole. Maybe I'll put it in black. So r is always going to be 1, little r. I always call this little radius, lowercase r, the smaller one. And then the big radius, capital R, will change. So the capital R Which color? I'm gonna use black one. Capital R will be very well visible here or there, right? Capital. And it changes because it varies. It depends on the values that come from the function. It depends on the x values because our capital R, the big radius, has something to do with x, right? And what does it have to do with x? So it is here in that particular case, and looks like I need to take 5, right? Let me do it here so it's not messed up. Things up. So I have to take 5, and from 5, I need to subtract x. See what? Well, let's check this out carefully. Do I subtract x or what do I do? Maybe not. Let me double check. Let me make sure. So this is going to be the point that I can get from my curve. So my curve, let me get it bigger. The curve is graph of that beautiful parabola, which is x is equal to y squared, right? Y squared. Here's so it varies. The point varies, radius is also vary, but the point has coordinates always the same, xy, right? X for the x coordinate, y for the y coordinate. So x is here. Please notice that 5 is here. So 5 is a distance to this axis of rotation from my y-axis. So 5 is center kind of rotation. And then we take this little x and subtract it. So if I have value of x in here, that's my x. I need to cut it out. I have to subtract it from 5. See, that's, I guess, the key moment. That's a new part in this exercise. That's for us to think over the weekend. Don't worry, I'm going to do more exercises next week that have same setting, so we'll get used to it because that's standard. So anyways, 5 minus x, and since my variable of integration is y, I need to replace my x with y, and here's the way to replace it. It's always coming from the function, so I have to use the 5 minus y squared. That's what I have to do. So that's my big R, capital R. So I found my radii and the little radius and the big radius. So what do I do now? Well, now I have to use my disk or washer, whatever formula. The disk area was pi r squared, right? So it was pi, and then it was from big R, I have to subtract the little r. From pi times big R squared dy, I have to subtract pi little r squared dy. So the big R is now here, so I just plug things in. It is 5 minus y squared. Don't forget that it's r squared. So whatever r is doesn't make difference for us. It is squared. Minus little r squared. And what do I square here? Well, the little r is 1. So that's something I like. At least that one I like. So we've got a good start. And we sounds like that. And now I just need to do algebra. Now I need to work out the square and etc. And that was the plan. So why don't I work it out? So square, that's first thing I'm gonna take care of. square on the outside. So you have to square first term, remember the formula for the difference of two squares. 2 times 5 is 10 multiplied by y squared. And then we need to add y squared squared, so 2 times 2 is. And say, what is that you're doing, Alex? I'm using the formula here. The one that's probably one of the most popular in algebra classes. So it's for the difference of 2 will be a square of first minus 2 times first times second, and then plus a square of second, e squared. That's what I'm utilizing right now. And that's what I did. So a square of first, 25, 5 squared, minus, because subtraction, 2 times 5 times y squared, 2 times 5 is 10, and then add, right, plus y squared squared, which is 4. When I say y minus, well, multiply by a minus b by another a minus b, you will see. So anyways, you don't have to use the formula. You could just multiply the parentheses with itself because it's square and you get the answer. So what is that am I trying to integrate? Well, looks like it will be minus 24. So I need to move to the other side and that way. So I guess at this stage, I probably should stop because the rest is standard. The rest is what you should be able to do without me wasting your time. Well, I can do it once for fun. So looks like we have to integrate what? 25 minus 1 is 24, and then minus 10y squared, and then plus y to the first. And of course, dy. I say, what if it was dx? Well, if it was integration with respect to variable letter x, then your function would change because you needed to pull out y. This would be dx, a function of x, and then you would need to change your limits of integration. In fact, that's what we're going to do next time. We'll do exercise with respect to x and then also integrate it with respect to y. That's what next section actually is talking about, because in 3 dimensions, not everything is so nice as it is in 2 dimensions. Right? So anyways, 24x. Let's say, what do you mean not nice? Well, I guess it's gonna be just the, not x, it's y. It's so easy to mess up. So that'll be cube over 3. So anyways, I was trying to say that's not nice because sometimes you can integrate, but sometimes you cannot. And that's why, so that was y squared and the other was y to the power of 4, right? Yeah, that's better. So point is pi stays on the outside. We'll put it at the very end. And my limits of integrations are from -2 to +2. Or some people might go some 0 hours like myself. Alex, I use 0 hour. Yeah, for this class, of course. Because notice that this is like a symmetric figure if you look at it with respect to x axis. Because if you reflect one part and the other, they'll be giving you the same thing with respect reflect to x-axis. So I could technically have a half of it, so I'll double and use 0 for one of the limits. You see the trick? It's gonna save you time because if you love 0, like myself, plug it in 0 instead of y will definitely help you a lot, because it's definitely gonna kill the lower limit results. But you need to not forget to keep it as twice. So that's something you don't have to do, but I would recommend you for simplicity of calculations. But one says, Alex, I love challenge, I love my calculations not to be simple. Well, the only thing you're risking with is to make a little mistake. And when you make a silly mistake, well, it is giving you completely different answer. But I usually check the work of my people and of my students, and then I will be not really punishing you for a mistake. I usually put like a minus. That's not really worth anything, right? Because in this class in our college, we don't have minuses. Like you get B minus, it means it's B anyways, right? So, but for you to know that it is not really perfect, it could have been better. But I never punish my students for arithmetic. But now notice that zero, if I plug in, then all of them become zeros because it's times zero, right? And that's why I subtract zero. That's why I like it. But now we have a problem. We have denominator. It's not a big problem, but it's still 15, right? I need to multiply by 15. So here and here, multiply, divide, and second fraction 5 to produce 15, so multiply it by 5, and the last fraction by 3. I think this will be the fastest way. I'm sure you're very good at arithmetic and you have your own ways, but I'm just trying to show you the way that I think it is working well, because after doing quite a few of these exercises, I think it's faster. So I'm trying to show you the fastest way, and I don't expect you to do it fast, because the faster you do it, the less chance you have a mistake, the less steps. Not really faster, but the less steps. So now what I do is go for the calculator, because all that numerator stuff I'm gonna just put in the calculator. I don't want to mess up with arithmetic. So favorite scientific calculator, and I'll just put in my numerator. So I use Desmos. I don't want to use Google one. It's not very convenient. It's free scientific Desmos. I think it's the best that I saw so far. We use it for statistics heavily, and it's nice because it shows you everything that you put in it, such as, so 2 I put on the outside of parentheses, and now I'm going to put whatever is inside of the parentheses. 24 times that 2 times 15, I know it's 30, so I can just 30. And then minus, now 10 times 5 is 50, which is also multiplied by 2 cubed, which is e. Or you can put whatever you like, but just trying to do convenient for me. So now plus 2 to the 5th, it's 32 times 3. Well, let me just put 32 times 3, like that. So there we have the answer. 832 over 15. I say, can you reduce this? Well, 15 is 3 times 5, so it definitely cannot be divided by 5 because it ends with a 2. By 3. Well, 3 and 2 is 5, plus 8 is 13. So sum of digits is 13, so it cannot be divided by 3. So that's our answer. I think in the textbook at the end, they give the answers, and they all in terms of fractions, so that's standard result. So I hope it is enjoyable, and I want to tell you one thing about the rest of the section. So the rest of the section, back to the book, that we can find the volumes not just using rotational produced figures, because that's quite specific, right? The other popular kind of figures is just like a pyramid we have here, or other things. Let's say that's also like a pyramid. Well, let's say pyramids. Well, here is not pyramid. Here is the one that is produced by some kind of parabola-like functions, right? So the point of the story that you can find the volumes of figures that were not rotation, so that pi r squared thing is not being used. But slicing method, analogous to the one that we utilized before, which is slicing with disks. Now we don't have disks. When we slice, we have a square or a rectangular or some other things. So what you need to use is analogous procedure. So thickness, if you slice along y-axis, will be thickness with respect to y. I say that looks like more like x-axis to me. Well, whatever it is, the name of x is that be your thickness, delta, they say y, okay. Because in general, the reason they do it here is because when we deal with 3 dimensions, it's not for our class, it's for Calc 3. They have x, y, z, that's how the axis usually being marked for a 3 dimension, because there's 3rd dimension, z axis. So that's why they put x-axis like that. Well, here's x, here's y. So anyways, we're not going to worry about it, but the point of story is that if you know the area of that square or whatever you have in the cross section, you multiply it by the thickness delta y and you get the value you need, and then you add all these thicknesses together, and that's how you get the limit of sum. So let me maybe trace one of these examples here. I don't want to spend much time on this. It's not very popular, but it is interesting, right? It is interesting. So you see there are lots of various figures that you can find volumes of now using the cross sections. So they given us the slicing along x-axis. So now it'd be along x-axis. That's why x-axis. So that's integration dx. That's the one that you can put right away. And how does x vary? Well, it looks like we start at 0 and we end at 2. So that's why it is 0 to 2, according to picture. And see, Alex, looks like that's what they have here as well. So 0 to 2, right? And dx. And what's happening now? Now I need to know the area of the cross section. The area of this triangle, which is base times height of this triangle. Or you could use trigonometric formulas, but I think it'd be too much because we don't want to use trigonometry as long as we must, right? So the area is base times height and times 1/2, of course. And then we also multiply it by delta x, and that's how it's all being done. So base times 1/2. So they found what base and what height was. So looks like now they are looking at this triangle on x and y axis. See, it is time consuming now. So we need to be able to find the area of triangle using the base and the height. So what are they using in here? What do they call as base and the height? Well, here's one function, 1 minus x squared minus x over 2, so that's the 1. So at any point x, since we integrate along the x-axis, so we break it into these little rectangles, my base, which is here, right? And my height will be there. And looks like for the height, right away I can say it's a value of function f of x. And that's why for the height, they're using this 1 minus x squared minus x over 2, 1 minus x over 2. So where's the area? I don't even write it. Well, anyways, height is 1 minus x over 2. See, that's where confusion comes. They don't write it exactly. So even though you have a solution, you need to get a piece of paper and a pen, and that's what I'm trying to show you right now. So you really want to understand what this means. So it's a base and then the area. So how Do you know that base is produced times what? How do you get the area? You need to multiply base by height, right? And then take 1/2. So height is here, and that's y coordinate, right? And y coordinate is exactly given to me by the function because f of x is the same as y. So that's the one that we have. And what about base? For what? For this triangle, right? So how can I find that out? Well, looks like I need to now be a little bit more careful. Let's see, it's 1 minus x, subtract y minus x over 2. So what are they talking about? Well, let me get another color so we better see what they're talking about. So 1 minus x over 2, that's y coordinate. And then from it, you subtract minus 1 over x over 2. So they subtract the other one. So why would they do that? So the triangle has the base here. So maybe I can refer to base on the picture so that way it'll be a little bit better. So where is this triangle, first of all? So triangle is here. So please notice that it's doubled. So what is double? Y, and there is another y. So you could just set 2 times y, and that's what 2 times y or 2 times 1 minus x over 2. So that's 2 times 1 is 2, and x over 2 minus 2 is over 2 times 2 is that. So I don't know, you could add one to the other, or you could just say twice. So now we're clear what the base is, right? So what's the height of this triangle? Well, the height of this triangle is right here, right? So how can I find that height now? Well, the height is going to be, they say, so what do they multiply? So how do they come up with area 1? See, that's interesting. Because the base is here. So they multiply square root 3 over 4, right? By another base, 2 minus x. So that's our height. See, they don't really say it at all. And that's our base. And please notice it has to be over 2. So they actually hit it here. So it's this one is over 2. And then they take it 1/2. See? So bases. So the area is 1/2 times not square root 3 over 4, but square root 3 over 2 because it's 1 over 2. So that's how it gets 4. So where did they write the height is that one? Well, they did not. Right? So that's part that they are missing. And maybe that's a good part for you to think about. So why the height of that triangle will be a square root 3 over 2 times that. So I think that's interesting to figure out because that's the square. So the picture here, we have base of that triangle, but what about height? See what I'm trying to ask you? How do I find the height of a triangle if it has equal sides? So the trick here is it is equilateral, right? So all sides are equal, like what? Well, I can say A, and A. So what's going to be the height of this? Well, maybe you use Pythagorean theorem and they say it's a square root 3 over 2 times A. Right? Let's say over 2, and A over A. See, there's a missing part. That's what I'm trying to show you right now. Because that's half, it's A over 2. And if you're using this little triangle, see, you're expected to know that. So how about finding the height h? Well, Pythagorean theorem, h squared is going to be equal to a square root from hypotenuse subtract a square of side. I told you to do this yourself, but I'm doing it for you. I think I love it, I guess. But anyways, maybe you'll do yourself some other one. So when you do the arithmetic, notice denominator is going to be 4. So you multiply by 4, top and the bottom, so 4a squared minus 3a squared minus 1a squared. 4 minus 1 is 3, and then a squared. And that's where you get the fact that your height is square root 3 over 2 times a. So they don't say it, but they use it. So square root 3 over 2 times a. So that's the one I multiply. And then I multiply it by another base, which is by another 2 minus x. And that's how I get 2 minus x squared. 2 minus x is squared, and then square root 3 over 2, because it's multiplied by 1/2, because it's for the area of triangle. So it is tedious. The point of story, if I start to get into all this, it's going to take a while. So we're going to do geometry now, and you can just see the ending of the story. So when you take that and when you integrate it, you end up with our number without any pi, because we didn't have any rotation. But I think it's one of the good examples that show that you don't just use these ideas for the rotational, but you can use it for anything. And this is great. I think that's enough with this section because we got stuck with it. But guess what? We're not going away from this story at all, because we're going to do more rotations, as I promised. And I'll be able to integrate and with respect to x variable and the same exact exercise with respect to y variable. And to be able to do this, I'm going to check out the next section. I know it's getting overwhelming, so I'll do one exercise just to show you how you could do the same volume thing differently. I think this is the nicest picture right there. It's extremely hard for me to make it. So let me clean the mess. So here's the picture I like. So anyways, we have been looking for the volumes, and if you, I need to take another color. So if I take another color and copy exact same figure here, then we used to find the volumes by making slicing of this by disks, right? So if I slice this volume by disks, and along x axis, right, from A to B, I'm going to integrate, and this will be radius, right? That's what we did before. So the integral from A to B, and then pi times square of this radius dx. That's not what they want. They don't want to do dx. What they want to do is they want to do dy. See, why? What's wrong with x? Well, sometimes when you have a function put here, you cannot find antiderivative. Cannot. And we might see an example next time, but the point is they do different integration. They integrate with respect to another variable y, because that might help you to get your integration to go nicer. So if your y is varying like in here from 0 to whatever number, they say from C to D, so they say in general they put C and D, but usually if it's rotated about the axis, then we go 0 to, let's say, D to D. And with respect to y, so now what we do is we slice this with cylinders. So I say, what is this figure? Well, important moment. Cylinder is here. And inside of this cylinder will be a cylinder or smaller. Actually, this would be of larger height. So the height used to be that. Now height is a little bit higher. And then inside is going to be another cylinder. It's like a pyramid. One cylinder inside of the other cylinder, and more of those cylinders. So they slice in with respect to the cylinders. They have a picture where they have lots of cylinders, put one inside the other. But I hope you got an idea. So you slicing it with not discs, but with cylinders. And those cylinders are going to have those cylinders are placed one inside the other. Well, let's see, why would they do it? Well, because they can integrate this way with respect to another variable of y. And what they want to do now is they have to cut this cylinder open. So they make a cut of that cylinder. So its height will be somewhere here, and that's your height. And the height will be with respect to x-axis, so that'll be value of x. That's your height. The cylinder. And if you cut it open, that'd be open to a big piece. So your circle here, your circle, when you cut it open, will be 2 pi r. The circumference of this, so that's radius r, and you have a circle. Its circumference, it's 2 pi r. My little son has candies, so you just, it's in the round, like a disc type of a box, and then he gets them out, it's like red candies, and opens, and it turns, the cylinder turns into open this nice piece, and we probably saw something like that, right? So anyways, the point of story, we cut this with cylinders, and then we have them open, and those areas will be 2 pi r times the height, which is in this particular case is equal to x. And that's what they have, 2 pi. And then the radius is here, and that's h of y, which is x, like that. And again, because we can change variable of our integration. That's why we're doing it. So I guess this is the idea of the section. So we can also slice it with the other, I guess, with the other shapes. And that way we will bring ourselves to the other kind of integration. So I'll do one exercise. I think that should be good enough, because Otherwise, it'd be a little too much, but I'll take something nice, maybe exercise 5 for starters. So this way we can see the process. So that's the next section, 7.3. And technically, if you know how to do one exercise from this section, you know how to do all of them because they're all the same. So once you understand and follow this slicing procedure, then, well, it's just standard for everything. So you have parabola x squared. So main thing is to make a picture carefully. So I take parabola x squared, the favorite option. And then we need to also have y is equal to 0. So y is equal to 0 is x-axis, right? Equation of x-axis. And then x is equal to 3. So that's a vertical line that so that's equation of vertical line x equals to 3. Okay. So it's good to, of course, realize that at x equal to 3, when you square it, it'd be 9. We may have to use it. So y is equal to x squared, so 3 squared is 9. So it looks like these 3 curves will produce this slice in their intersection. You say, Alex, who told you this slice? Well, look at them. There's only one part, only one region of xy plane, which is bounded by those 3 curves at the same time. So that's what they expect you to figure out. And now your data is about y-axis. So that's important to realize that when you rotate this about y-axis, you're gonna get something like that, right? So the figure will be like, again, a nice cylinder, but there is a portion of it is cut out, so that inside is cut out. I don't want to put any more mess, but that's what is going on here. And then what they want us to do is to find the volume revolving using shell method. That's what they want us to use. So they tell us what to do, because otherwise I would slice it with washers. So we did it already in the previous section. So I will now slice it with shells. So how to slice it with shells? Well, how do we produce those cylinders? It will be here. Shells here. So my shells will give you integration from 0 to 3 with respect to axis. So you cut with your cylinders only that piece, because that will be rotated and produce the other piece of cylinder. So dx is my variable of integration, x. Please notice, if you did it with washers, you will be slicing it from 0 to 9 and did dy, which is also possible. In fact, I think that's probably even better, but we need to do dx here, so let's do it. So I need to think of that cylinder, so let me get that little green cylinder separately. Better see. So that's our cylinder with thickness delta x. Of course, it goes along the whole thing. Thickness. So the height, notice the radius is here, and my radius is going to be nothing else but x, isn't it? So whatever x coordinate is going to be the radius r. For that cylinder. That's good to think about. So radius is r. And there is a height. And notice the height is y coordinate. So my formula is 2 pi r multiplied by x. So 2 pi always take on the outside. And then what is the radius? Well, we just saw it is x. And what is the height? Well, the height here is given to me by the y coordinate. And y coordinate is x squared. One can say, Alex, you didn't really need parentheses, but that's my height. Not bad, right? For the integral, it's pretty straightforward. So let me finish up with it and we'll get the answer. And maybe end at this stage, right? So you have to integrate x cubed. Right? It is x cubed. And the antiderivative of it will be x to the fourth divided by 4. X cubed, and we go from 0 to 3. Well, my favorite little friend 0 is here. I really love to see it again. So cancel 4, we get 2. And then we get pi over 2 leftways. And then the upper limit is going to be 3. So it will be 3 to the fourth. And the lower limit is 0. So it's a 0 to the fourth. And we end up with 3 to the fourth, which is 81, right? Pi over 2. So with 0, as usual, it's very nice calculation. If you want to do the slicing with respect to the other variable, little letter y, let me do it. Let me do it. I say, Alex, you said that's it. Well, let's give it a final little push. So that was pi r squared. So I do the same thing, but differently. Pi r squared. So what is that I need to square? What is going to be my radius of rotation? So say, Alex, that's the same radius that you just utilized. So the radius was x. Yes, but it's dy. So I need to replace my x with square root of y. Okay. I can do that. I can replace it with the square root of y. And that's even better because now I square. So I need to go pi r squared. So I go, what is this? It's pi r squared, right? We put 2. Say, Alex, that's you. Well, I'm getting tired then. So it's definitely time for a break, right? So it's pi r squared. I gotta put pi r squared, and we're integrating it from, again, slicing goes from 0 to 9, right? Did I put 0 to 9? Put something else. 0 to 9. Yes, I got carried away. So 0 to 9, again, why is it 0 to 9? Because we slice this with disks, right? But there is a disk on the inside. So it's a big R minus a little r, right? And the little r is what I just found. So maybe I need to be a little bit more careful. Write it again. So pi r squared. So again, what is the big R? Big R is 3. I think it'd be a good idea for you to double check all that on your own. 3 squared minus little. And the little r is what we saw, and that was x, and instead of x, we put that square root of y. And since it was squared, so the y is only thing that remains. Okay, so now you're going to need to integrate 9 minus y, and that's pretty nice and standard. So we end up with a 9y, subtract y squared over 2. So it is also nice integration, so it doesn't matter which value you use, x or y. So as promised, I'll give you the next time quiz. I will ask you which one you're using for this particular exercise, but I guess we're not ready for that quiz yet. So now I plug in 9 for y's, and that should be my answer, because when I use 0, it's 9. Instead of x, it all becomes 0. So 81, subtract 81 over 2. So you end up with 81 over 2 times pi. Okay, Alex, you got the 810. Why did I get 810? It's 81 pi over 2. Yeah, it is the same thing. 81 over 2. Okay. So again, I got lucky because both answers are the same. So it doesn't really matter. It shows us it doesn't really matter which way you do the exercise. The answer is the same, 81 over 2 pi. Of course, you don't want to do the same exercise twice. It is pure waste of time. And I'm not wasting your time. I'm showing you that it is up to you how you do the exercise, integrate with respect to x or with respect to y. So to give you a confidence. So you might say, so Alex, I just learned section 7.2 and forget 7.3. Technically, yes, but with integrations, it's not always nice thing, because sometimes you cannot take the antiderivative. But to be honest, when I'm looking at these functions, they all should be either quadratic radicals, so you can do substitution, so you can take antiderivatives for all of them. Of course, at the end of the section, you might encounter exercises that you have to use only shells, or on contrary, only the washers. So that way you don't have a choice, you need to try. But here it doesn't matter how you started, and that's what's called easy exercise. No matter how you started, you get the answer, and everything is fine. So anyways, thank you so much for paying attention. I think I better stop at this stage, and I'll start giving little quizzes next week. I think that'd be a good idea, because I see that not many students are here, and that's fine. That's fine, because I do recordings, so you can, of course, watch it over during the weekend or during the next weekend, which is fine with me. As long as you get these ideas before the midterm, it's absolutely fine. Because for the midterm, I will check and see how you're doing, and exercises will be standard. What can I possibly ask you to do? Well, exercise like number 5. Everything pretty straightforward. So you already know how the midterm is going to look like. I'll give you an exercise like number 5, and I'm sure you're all going to do it just fine, right? But anyways, you still want to make sure that you get a piece of paper, pen, and write it down. So for the homework, remember, I'll ask you to just copy one of the exercises. So I think 5 is good, and you can copy just 1/2 of it, either with washer or solution with shells, whichever you prefer. But and that will be your homework that you will be emailing to me on the day of the midterm. So you don't need to email it to me over weekend. Just wait. Don't lose it, please. The homework you should put together in 1 or 2 or more emails. Just make picture, attach it, and send it to me. But I want it to be complete. So when we are done, when we come to the midterm time, then I will, of course, remind you to email all your work, and you will get credit automatically. I think it's not hard. Just make sure that you keep up with us. Just copy the same thing on the paper. All right. So I guess it's time to stop. So I will stop and have you enjoy the rest of the day and have a great weekend. So thank you for checking in and